Welcome to Tomorrow Unveiled. If you are at the future, you know that space isn't really just the domain of distant exploration anymore.
Not at all.
It's become this arena of, well, really urgent operations. And the week spanning November 19th through the 26th, 2025, it just provided a staggering amount of evidence for that.
It really did.
The industrialization of space is accelerating, but that acceleration is now running headlong into crisis.
It was a truly defining week. I mean, the capability gains we saw were just monumental.
Right.
But the systemic fragility, that became undeniable. The fundamental narrative, it wasn't just about a successful launch here or a failed test there.
Yep.
It was about the systems. The systems needed to sustain permanent, large-scale operations and, maybe more critically, to manage failure, to contain the growing risks of a, frankly, overcrowded low Earth orbit.
And our mission here, as always on Tomorrow Unveiled, is to take this huge stack of sources that our dedicated research team compiled this week. The articles, telemetry data, official announcements.
Just a lot of material.
It is. And we want to extract the most important corroborated nuggets of knowledge for you. We really aim to offer a rapid shortcut to being truly well-informed about where this is all going.
And we've synthesized that sheer volume of material into three, I'd say, dominant interconnected themes. They really define the current trajectory of the whole space economy.
Think of them as narrative arcs.
Exactly. The three narrative arcs that are going to shape the next decade of activity in space.
So first up, we have the operational crisis. I mean, a severe, just undeniable threat posed by space debris that forced an emergency response unlike anything we've ever seen.
We are talking about a crewed rescue mission.
All because of something the size of a grain of sand. It's high drama.
Yeah, absolutely. Then second, we pivot to the infrastructure race. This is the big shift toward treating space like a service utility.
Right.
So we're seeing tangible steps toward true in-orbit servicing, standardized refueling, autonomy. It's all proving that space is moving from a high-risk exploration zone to a sustainable industrial complex.
And finally, heavy lift competition. The fierce, costly, and, high-risk battle for launch dominance.
And this week was just a perfect snapshot. A massive, high-profile technical setback for one industry leader.
Followed immediately by an aggressive, capability-defining upgrade from its main competitor.
It's a race that is just fundamentally restructuring the economics of getting to the moon and Mars.
We're going to unpack some really deep technical details. Things like the forensic analysis of a spacecraft window crack.
To the immense engineering challenge of transferring, supercritical xenon gas in microgravity. And some of the fascinating economic calculations that actually led to the cancellation of a high-profile nuclear propulsion program.
Okay, let's unpack this.
Yeah.
And we have to start at the highest possible drama, the crisis in orbit.
The most dramatic, high-stakes event of the week really belonged to the Chinese space program. And it serves as this stark, visceral reminder of the growing fragility of our VLEO infrastructure.
This was the first emergency crewed spacecraft launch in their history, right?
In the program's history, yes. The uncrewed Shenzhou 22 spacecraft. This was a rescue mission, plain and simple.
And what makes this so critical, I think, is that it was a response to damage that was tiny, just physically tiny, but with these potentially catastrophic consequences for the crew on the Tiangong space station.
That's it.
What was the exact cause of the emergency?
The emergency stemmed from a debris strike. It was discovered earlier in November.
Okay.
The target was the return capsule of the Shenzhou 20 spacecraft, which was docked at the station. It's essentially the crew's primary way home.
It's their lifeboat?
It's their lifeboat. And the research team that compiled this for us, they indicate the damage was to the window. It was likely caused by a micrometeoroid or a piece of space junk, maybe only sub-millimeter in size.
A sub-millimeter fragment. So we're talking about a paint fleck, maybe? Aluminum dust?
Exactly. Something that small, yet it generated enough force to endanger 3 highly trained astronauts.
You really have to visualize that for a second.
Absolutely. You have to remember the physics of orbit. That tiny object, it struck the window at orbital velocity. So that's between 7 and 8 kilometers per second.
Unbelievable speed.
At that speed, the kinetic energy released is just enormous. It's comparable to, if not more than, the energy of a projectile from a high-caliber rifle hitting that window.
Wow.
And the result wasn't an immediate breach, but a severe propagating crack in the glass.
So the crew Zhang Lu, Wu Fei, and Zhang Hongzhang, they were safe while they were docked.
For the moment, yes.
But the vehicle itself was instantly useless for its main job. Why? Why would a cracked window, not a full hole, required a whole new capsule.
It all comes down to the stresses of re-entry, the thermal and the mechanical stresses.
Okay.
When that spacecraft plunges back into the atmosphere, it's slowing down with friction, generating just colossal heat. Temperatures on the outside can exceed 1600 degrees Celsius.
So like a furnace.
Exactly. And the window assembly, even if it seems structurally sound in orbit, it relies on total integrity to handle that thermal load and the pressure differential. A compromised window, even with what looks like a hairline fracture, would fail catastrophically.
And superheated plasma would just enter the cabin.
Instantly, it would incinerate the crew. So the Shenzhou 20 was immediately certified non-reentry capable, and the crew was left without a lifeboat.
The moment that damage was confirmed, the clock just started ticking. It's a life or death decision.
It is.
And this is where the Chinese National Space Administration, the CNSA, showed a capability that, well, it frankly shocked a lot of observers.
The response was just a masterclass in responsive space logistics.
Yeah.
They launched the uncrewed Shenzhou 22 on a Long March 2F rocket.
And the numbers here are what's incredible.
2 data points are just mind-blowing. First, the speed of rendezvous. It docked just 3.5 hours after launch.
3.5 hours, so they minimized that window of vulnerability.
Greatly. And second, the preparation timeline. This standard procedure for readying a human-rated rocket and capsule is about 45 days.
Okay.
The CNSA got it done, full mission readiness, and launch in just 16 days.
16 days to assemble, fuel, test, and stack a vehicle that is literally meant to save human lives. That is a blistering and unprecedented pace for a crewed-class system.
It is.
And our research team highlighted that this speed was only possible because of something the industry calls the rolling backup doctrine.
That's the strategic key. The rolling backup doctrine means that for every crewed mission they have in orbit, China maintains a second Long March 2F rocket and a Shenzhou spacecraft, fully stacked.
So just sitting there ready to go.
Kept in a state of high readiness, essentially at a T-minus 8 days status at the Jiuquan Launch Center. It's a massive, costly investment in redundancy.
So they're paying for an entire certified crew-capable system to just sit idle, basically waiting for a disaster.
That's right. And this week, that very costly redundancy proved its strategic value.
So this raises a really important question. If NASA, or say the European Space Agency, faced a similar situation with their crewed capsules, could they launch a rescue vehicle in 16 days?
That is the uncomfortable question, isn't it? And currently, the answer is no, not reliably.
Wow.
I mean, while NASA relies on the dual redundancy of Crew Dragon and Starliner, or historically on Soyuz,
Right.
they don't maintain an integrated, fully fueled, crew-rated system on the pad, ready for an immediate rescue launch. This capability from China, it really shifts the metric of power in space.
It's no longer just about who can launch the heaviest payload.
It's about who can respond fastest and most reliably to a crisis in orbit. That's a new game.
And it also tells us something about their operational priorities, because the Shenzhou 22 wasn't just a taxi service, was it?
No, it served a dual purpose.
What else did the research team find in its cargo?
Well, its primary role was absolutely rescue. But it also delivered critical supplies. This included spare parts for the station, specialized medical supplies, and even fresh groceries.
And a space oven, I read?
And interestingly, a space oven. It just shows that even under that kind of duress, maintaining crew morale and long-duration living infrastructure, it's an integral part of high-stakes space logistics.
Let's shift from the anecdote, from the Shenzhou 22 to the systemic problem. Because this single incident, it validates the absolute worst fears about the space debris crisis. You know, what people sometimes call the Kessler syndrome.
It absolutely does. This was the first publicly confirmed debris damage to a crewed spacecraft that required an emergency launch response.
So the threat isn't theoretical anymore.
It's fully operational. I mean, data compiled by organizations like the European Space Agency suggests there are approximately 1.2 million objects larger than 1 centimeter.
1 centimeter.
Currently trackable in low Earth orbit.
1.2 million.
Yeah.
And any one of those, if it hits a critical asset, a satellite, a window of the solar panel, a fuel tank, it can create a cascading failure.
And the situation is accelerating exponentially.
Okay.
The global launch cadence is just skyrocketing. Our research team found that 2025 saw over 273 successful orbital launches.
And that's up from 259 in 2024.
Exactly. So as launch rates multiply, the conjunction risks, the probability of 2 objects trying to occupy the same space at the same time, they grow even faster. Every single launch adds both active satellites and, well, future debris.
We're rapidly approaching a point where the debris field gets so thick
That collisions just generate more debris, and that could make certain orbits completely unusable.
that structural threat, then that increasing fragility of LEO, is really what makes our next segment so crucial.
It is.
We're talking about the infrastructure required to sustain operations and, I guess, to mitigate that very risk.
The crisis we just discussed is precisely the driver for this next theme. I mean, space is transitioning. It's moving from a high-risk exploration zone to a sustainable industrial utility sector.
And that shift demands infrastructure.
Standardized infrastructure for maintenance, for life extension, and for refueling.
So the days of launching an incredibly expensive satellite and then just watching it die because it ran out of fuel, those are ending.
They have to be.
The paradigm is changing from launch, use, and dispose to launch, use, service, and reuse.
And this is being led by a commercial sector that sees a massive business opportunity in saving, billions of dollars worth of aging government assets.
A clearest example this week has to be the Catalyst mission.
Yes. This involves an aging asset, the NASA Neil Gehrels Swift Observatory. It was launched way back in 2004.
An old-timer in space terms.
It is, and it's slowly spiraling toward a premature reentry just due to orbital decay.
So Catalyst Space Technologies, they secured a contract to autonomously rescue it. Walk us through the plan for mid-2026.
Okay, so Catalyst plans to launch a dedicated orbital tug. This vehicle will autonomously rendezvous with the 20-year-old observatory.
Which is a huge technical challenge in itself.
It's incredibly complex. Then it will inspect the structure, securely grapple this non-cooperative satellite, and then perform a major orbit boost.
Putting it back where it's supposed to be.
Exactly, restoring it to its original, productive 600-kilometer orbit.
If they pull this off, this isn't just a technical win, right?
Yeah.
It's a profound validation of a whole new commercial business model.
It would be the first private capture and life extension of an uncrewed U.S. government satellite. It proves that commercial companies can offer satellite operators, both government and private, a cost-effective alternative to just replacing everything.
Right. Why spend $500 million replacing a telescope that still works perfectly when you can pay a fraction of that to just give it another decade of life?
That's the business case.
So orbital servicing is one key. The other has to be standardized refueling.
It is.
Which brings us to Europe's major announcement this week, the ASTRO contract.
Yes. The European Space Agency announced the Advancing SATCOM Technology with Refueling and Logistics, or ASTRO contract. The initial funding, £1.3 million, it might seem small.
Especially compared to the billions spent on heavy lift rocket.
Right. But its strategic importance is huge. This project is explicitly aimed at establishing Europe's first in-orbit refueling demonstration, and they're targeting a 2028 deployment.
And the centerpiece technology, the thing that enables this future economy, is OrbitFab's RAFTI.
That's the crucial standard. RAFTI stands for Rapidly Attachable Fluid Transfer Interface.
So it's like a universal gas cap for space.
That's the perfect analogy. For the orbital refueling economy to work, every satellite, no matter who builds it, needs a uniform port. This technology is trying to solve that standardization challenge. It enables gas stations in orbit.
But the ASTRO mission isn't just about docking and pumping, is it? The research team really emphasized that the propellant they chose, Xenon, presents a really specific, really difficult engineering hurdle.
It does.
Why is transferring Xenon along with nitrous oxide and ethane so uniquely challenging in space?
Okay, this is where we get a little technical, but it's critical. Xenon is the lifeblood of the high-value commercial space market.
Why is that?
It powers Hall-effect thrusters and ion engines. Those are the primary propulsion systems for almost all modern geostationary telecom satellites and the LEO mega-constellations. So if you can refuel with Xenon, you can extend the lives of assets that are worth, collectively, trillions of dollars.
Okay, so if it's that valuable, why is it so hard to transfer?
Because Xenon is not stored like your typical, easily handled liquid rocket propellant. It's stored as a supercritical fluid.
And what does that mean?
It means it's above its critical temperature and pressure, so it has properties of both a gas and a liquid. And it's at extremely high pressures, often over 2,000 psi.
And in microgravity?
In microgravity, where fluid dynamics are just weird, managing the thermodynamics of that expanding gas during transfer is incredibly complex.
You're dealing with a substance that, if you mishandle it, could freeze the lines? Or rupture a client's tank from a sudden pressure spike?
Or cause thermal failure across the whole system. It demands sophisticated autonomous flow control and extreme thermal management systems that just haven't been reliably demonstrated in orbit before.
So this technical success is the linchpin.
It is. If they master Xenon transfer, the orbital utility economy explodes. If they fail, that economy stays severely limited to, less efficient chemical propellants.
And linking this back to the Shenzhou 22 crisis, the Astral project has an explicit geopolitical and defense motivation, doesn't it?
It's a core component of achieving strategic autonomy for Europe. By developing a sovereign refueling supply chain, Europe ensures its defense and critical commercial assets can be maintained and maneuvered independently of U.S.-based providers.
Which is a huge strategic imperative in an increasingly contested orbit.
Absolutely.
That desire for autonomy and efficiency is also driving a profound shift in control systems. I'm talking about the rise of AI in orbital mechanics.
Autonomy is key for two very distinct scenarios. One, increasing efficiency in VLEO, and two, enabling true deep space exploration where human control is just impossible.
And in Germany, the LALAR project from the University of Würzburg just marked a world first.
They successfully deployed the first AI agent to autonomously control satellite attitude in orbit.
So it's an AI learning to fly a satellite.
By itself, using deep reinforcement learning neural networks with no human intervention. This moves way beyond simple pre-programmed control. The AI is learning and adapting based on real-time feedback.
And for deep space missions, this is essential.
It's a necessity. For a probe orbiting Jupiter, say, where communication delays can be 40 minutes round trip,
A human can't react in time.
an AI has to be able to recognize a trajectory deviation, diagnose a hardware fault, and execute a correction immediately. It's not a convenience, it's a requirement for deep space.
We're also seeing innovations aimed at just eliminating the need for complex refueling in certain high-traffic areas, like very low Earth orbit or VLEO.
That's the Redwire contract. They're focusing on VLEO satellites. Instead of carrying heavy, finite propellant supplies, they're developing air-breathing electric propulsion systems.
So they ingest the thin upper atmosphere.
They actively ingest the residual atmospheric air molecules and use that as propellant. It's like flying a satellite on air, essentially.
And that enables much longer missions.
Far longer mission lifespans in VLEO, which is a desirable orbit for high-res imaging and intelligence gathering. It dramatically reduces the need for refueling missions in that particular altitude band.
So the combination of catalyst life extension, ASTRO refueling, AI control, VLEO propulsion, it really shows this whole infrastructural layer is solidifying right now.
It's all happening at once.
And before we move on to the massive rockets that are defining the heavy lift competition, a competition that's defined by both huge successes and massive engineering failures, we have a quick moment for a note on engagement. If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
We love hearing your thoughts. Whether you're watching on YouTube or listening elsewhere, leave a comment and let us know what you think about the emergence of the orbital refueling economy we've just discussed. Do you think standardization like RAFTI is enough? Or is the difficulty of transferring Xenon still the critical hurdle?
Now, let's pivot to the behemoths, the vehicles that make all this possible, and whose development defines the current competitive landscape.
The heavy lift sector is defined by, speed, high risk, and just massive capital investment. And this week provided a perfect microcosm of that environment.
Starting with a high-profile setback for SpaceX's next-generation booster, Starship.
That's right.
Tell us about Booster 18. This was the first of the new version 3 Super Heavies. What happened at Starbase?
Booster 18 suffered a catastrophic structural failure during ground testing on November 21st.
And this wasn't even during an engine test.
No, not a static fire. It was during gas system pressure testing. Essentially, the liquid oxygen, the LOX tank, ruptured. This means the structure itself failed under the required operational stresses before the engines were even lit.
The research team noted this is the second V3-related anomaly in pretty quick succession.
It is. It followed a previous issue with Raptor engine integration. A structural failure like this, it tells you a lot about the design choices being made.
It points directly to the razor-thin margins they're targeting.
Absolutely. The failure highlights concerns about the structural integrity, particularly with the composite overwrapped pressure vessels, the COPVs, and the welds in the upgraded V3 design. SpaceX is pioneering the use of stainless steel alloys pushed to their absolute maximum yield strength.
To maximize performance, minimize mass.
They're trying to build the lightest, strongest tank possible. This failure suggests they momentarily crossed that line and found the structural limit forcefully.
What does a high-profile structural failure like this mean for the bigger strategic goals?
Yeah.
I'm thinking specifically of NASA's Artemis program.
It undeniably adds uncertainty to NASA's Artemis III lunar lander timeline. SpaceX holds that massive contract for the crewed lunar descent system.
And Starship is fundamental to that.
It's the whole architecture. Not just the lander, but launching the massive quantity of propellant needed for orbit refilling before the lunar injection burn. The setback, it introduces delays. It forces NASA to maintain contingency plans.
But the defining characteristic of SpaceX is always their rapid iteration. They're designed to fail fast and learn faster. What's been their response?
Immediate resilience. The company confirmed plans to stack Booster 19 soon, and they're maintaining their internal target of Flight 12 in Q1 2026.
So the fail-fast ethos is not just a slogan.
It's their operational model, but they're also implementing more caution. They're planning at least one suborbital flight for the V3 booster before they attempt orbital missions, just to thoroughly validate the structural fixes.
That setback, though, it provided a really opportune moment for their main rival, Blue Origin, to make a huge statement.
And they responded aggressively this week.
They did.
They absolutely capitalized on the moment. Blue Origin has been operating, much more quietly, prioritizing steady, incremental progress. And that progress culminated in two massive announcements about their New Glenn heavy lift rocket.
The first was the technical success, right? The booster landing.
Yes, the NG-2 flight successfully landed its first stage booster on the recovery vessel Jacqueline.
That makes Blue Origin only the second organization in history, after SpaceX, to successfully land an orbital-class reusable rocket booster. It validates their entire architecture.
It does. It validates their massive investment in reusability and recovery. And the second announcement was a declaration of capability.
The massive New Glenn 9x4 variant.
A super heavy configuration. The number 9x4 refers to 9 BE-4 engines on the first stage. That's an upgrade from the standard 7 and 4 BE-3U engines on the upper stage.
Okay, let's talk about lift capacity, because this is where the competition gets really serious. How much can this New Glenn variant actually lift?
The New Glenn 9x4 promises to lift a staggering 70 metric tons to low Earth orbit. 70. And the original design was closer to 50.
Correct. This upgraded capability puts it directly into the Starship class. This is not just a bigger rocket, it's a declaration that Blue Origin intends to compete for every single major heavy lift payload out there.
Whether it's NASA's lunar contracts, military missions,
or large commercial constellations, all of it.
Our research team consistently highlights that this competition between two highly capable, reusable heavy lift platforms, Starship and New Glenn, is the core economic driver of the future space economy. Why is that?
Because it creates genuine redundancy, and it forces cost optimization. When you have two private companies competing to deliver 50 to 100 plus metric tons to LEO, the market pressure drives costs down dramatically.
Not just incrementally.
Not at all. Launch costs start moving away from being amortized across a disposable vehicle and start approaching the marginal expense of just propellant and operations. And that fundamentally accelerates the feasibility of Moon and Mars bases, which require sustained, affordable logistics.
It's an economic breakthrough driven by engineering breakthroughs?
It is. But despite the Starship setback, we have to acknowledge that SpaceX continues to industrialize space access at a cadence that is unmatched by the rest of the world combined.
Their operational tempo is staggering. This week saw a historical milestone. SpaceX conducted its 150th Falcon 9 launch of 2025.
150.
Which means, on average, they've achieved an operational cadence approaching one launch every 2.4 days. This manufacturing and rapid operational throughput, launching, recovering, refurbishing, relaunching, that is their real competitive moat.
And within that 150th flight, there was a specific reusability record that really underscores their mastery.
That was the Transporter 15 mission. The booster, B-1071, flew for its 30th time.
30th.
Think about the engineering required to subject a single airframe to the extreme loads of launch and supersonic reentry 30 separate times, and then certify it safe for another flight just days later.
It's incredible.
Reaching 30 flights on a single booster, it validates their projections on fatigue life and radical cost amortization.
And the transporter missions themselves, they are a perfect snapshot of the modern space economy. What did Transporter 15 actually deliver?
It was a classic rideshare manifest. Over 100 satellites for more than 30 customers across 16 countries.
So all sorts of things.
You had synthetic aperture radar satellites for Earth Observation Company, ICYE, environmental monitoring payloads for GHGSat, which tracks methane emissions. The continued success of the transporter ecosystem, it just confirms that the rideshare model is now the primary standardized logistical backbone for the whole small satellite economy.
So while the commercial heavy lift race accelerates capability, the U.S. government's human spaceflight program faced a major reliability crisis this week.
Yes, a crisis that forced a profound strategic pivot.
We're talking about Boeing's Starliner program and a major downgrade of its future missions. What was the core decision announced by NASA?
NASA reduced Boeing's definitive missions from 6 down to 4. And critically, they converted the next flight, Starliner 1, to be cargo only.
Cargo only. That's a functional admission of serious operational risk.
It's a fundamental restructuring of the commercial crew program's near-term goals.
And this decision stems directly from the issues they found during the 2024 crew flight test.
That's right.
Let's dive deeper into the technical fault that caused NASA to effectively sideline Starliner for human transport, at least for now.
The primary issue lies in the reaction control system, the RCS thrusters. These are vital for maneuvering in orbit and for deorbiting safely. And post-flight analysis of the CFT revealed persistent unreliability, specifically linked to something called thermal soakback.
Okay, break down thermal soakback for us.
So thermal soakback is a complex physics problem in space. When the RCS thrusters fire, they generate immense heat.
Right.
In the vacuum of space, that heat doesn't dissipate easily. It instead soaks back or travels up the fuel lines and into the thruster valves and the propellant itself,
And Starliner uses hypergolic propellants.
which ignite on contact. So this excess heat causes the propellant to degrade, maybe vaporize, or chemically corrode the valves, which leads to them seizing up and failing.
And because ground testing in a vacuum chamber couldn't fully replicate that specific orbital thermal profile where the failures happened.
NASA decided they just couldn't risk the crew. They need an uncrewed flight to validate all the structural and thermal fixes they've implemented since the CFT.
The risk profile was just unacceptable.
Exactly. But the strategic consequence of this conversion is immense. It forces total near-term reliance on the SpaceX Crew Dragon for all human access to the International Space Station.
Which creates a single point of failure.
It does.
The entire commercial crew program was built on the premise of redundancy, making sure that if one vehicle was grounded, the other could maintain crew rotation. This completely undermines that core goal.
It creates a major national security and operational vulnerability. I mean, if a Falcon 9 anomaly occurred, grounding the Crew Dragon fleet for an extended period,
The U.S. and its partners would lose the ability to rotate crews.
and you could potentially be forced to decrew the ISS. On top of that, the economic fallout for Boeing is significant. They are absorbing over $2 billion in losses on this fixed-price contract.
And this reduction in guaranteed missions just makes it worse.
It further challenges the program's financial viability, and it raises big questions about whether that fixed-price contracting model even works for this level of technological complexity.
But the narrative of strategic space access isn't solely defined by U.S. successes and failures. The global landscape is expanding, and we saw a major milestone from South Korea this week.
It did. South Korea achieved a significant technical and commercial milestone with the 4th flight of their Nuri rocket. It successfully carried the CAS-503 satellite.
And while the launch itself was important, the strategic context is what really matters here.
It is.
That launch was the first Nuri mission led entirely by a private company, Hanwha Aerospace, right?
Yes. This is South Korea transitioning its launch capability from a state-run government enterprise to a fully commercialized private launch service provider.
And that's a massive strategic move.
It is. It's directly linked to their ambition to capture 10% of the global space economy by 2045. It just signals that commercialization is now the accepted, indispensable path to achieving strategic launch independence.
This confluence of engineering challenges, the need for high performance, cost-effective launch, and global ambition, it brings us to advanced propulsion, which saw a major strategic decision this week concerning nuclear systems.
Yeah, we saw simultaneous acceleration and cancellation in the realm of deep space propulsion. First, NASA's Advanced Electric Propulsion System, or AEPS, continues qualification. This system delivers 12 kilowatts of power.
Which is 3 times the power of current Hall thrusters.
Exactly. And that increased power is essential for the Lunar Gateway's power and propulsion element, enabling sustained high-efficiency operations around the moon.
But the big news was the cancellation.
The big fascinating news was the cancellation of NASA's Draco nuclear thermal program. It was targeting a 2027 demonstration flight. This was one of the highest profile projects aiming to drastically cut transit times to Mars. So,
Yeah.
why scrap it?
This is a perfect example of how the economic changes we just talked about in the last segment are rewriting the engineering calculus. How did the heavy lift competition impact a nuclear reactor program?
The key factor was the decreasing launch costs, driven by SpaceX's cadence and reusability, and now the rise of New Glenn.
Okay.
Nuclear thermal propulsion, or NTP, like Draco, is complex and expensive to develop. It was primarily justified because it offered huge performance gains, cutting Mars transit time by months, which reduced the overall life support and payload mass you needed for a mission.
But when the cost of launching that mass propellant, habitat, food drops dramatically.
The economic benefit of that extremely high-performance NTP system just shrinks.
So if it costs 5 times less to just launch the extra food and fuel for a slower chemical trip, the multi-billion-dollar cost of developing a brand new nuclear system becomes much harder to justify.
It shifts the focus. NASA's focus is now shifting to the Air Force Research Laboratory's JETSON Nuclear Electric Propulsion Program.
And how is that different?
Nuclear electric propulsion, or NEP systems, are slower, but they're far more efficient for deep space applications like cargo and tugs. They align better with the current economic reality of cheap launch. And the research team noted that AI is helping here too, using machine learning to optimize reactor geometries and heat transfer for these next-gen NEP systems.
Making future long-haul missions even more efficient.
Essentially, yes.
Finally, we should briefly acknowledge Europe's continued push toward independent lunar access.
Yes, the European Space Agency finalized the industrial team for the Argonaut lunar lander. They're targeting a 2030 launch, and Argonaut is designed for a hefty 1,500-kilogram payload capacity to the lunar surface.
So it's a serious lander.
It demonstrates that lunar logistics is now a truly global competitive market. It's not just a US and Chinese domain anymore.
The convergence of all these commercial successes and technical setbacks, it just reminds us that the path beyond Earth is defined by complexity and, well, calculated risk.
It really is.
If you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could take a moment, leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners and keeps us motivated to perform these deep dives every week.
And again, let us know in the comments or wherever you listen, what stands out to you about the geopolitical shift we're seeing? Does the Nuri success or the Starliner downgrade impact your view of global space leadership?
Now, for our final segment, let's look far beyond LEO and see how orbital technology is feeding breakthroughs in atmospheric flight and enabling future exploration on Mars.
As the space industry matures, the technology developed for orbital reentry and high-speed flight is creating these incredible spillover effects right here on Earth.
Driving breakthroughs in atmospheric travel.
The future of flight saw two major developments this week, illustrating two very different goals. One involves making supersonic travel quiet enough to be legal again.
And the other involves making hypersonic flight simple enough to be viable. Let's start with quiet. NASA publicly confirmed the first successful flight of the X-59 quiet supersonic research aircraft. Why is the design so radical?
Well, the X-59 is designed to revolutionize overland flight. Since 1973, supersonic flight has been restricted over land because of the sonic boom.
The noise pollution.
Right. The X-59's unique, long, slender airframe geometry is engineered to prevent the shockwaves from coalescing into a single loud boom.
So what's the target noise reduction?
The goal is to generate a sonic boom that is quieter than 75 perceived decibels.
And for comparison, what was the Concorde?
The retired Concorde hit about 105 decibels, which is like a nearby explosion. 75 decibels is more like the sound of distant thunder or a car door closing a block away.
So if NASA can prove this works at scale, it could provide the basis to allow routine overland supersonic flight again.
That's the goal. It would fundamentally alter commercial aviation transit times.
And on the extreme speed side hypersonic flight, Mach 5 to Mach 10, we saw a fundamental scientific breakthrough that simplifies the engineering challenge dramatically.
That was the validation of Morkoven's hypothesis at Mach 6. This is highly technical, but it's fundamentally important.
Okay.
Hypersonic flight has always been plagued by complex, unpredictable flow behavior turbulence that made engineering robust airframes extremely difficult and costly. This research confirmed that turbulence consistency remains fundamentally stable at these extreme speeds, contrary to some previous assumptions.
And why does consistent turbulence simplify the engineering?
Because if the turbulence behaves predictably, engineers don't need to completely redesign the aerodynamics or the control systems for every small change in speed or altitude.
It reduces uncertainty.
It dramatically reduces the uncertainty and stress in thermal modeling, which cuts development time and cost for vehicles moving 5 to 10 times the speed of sound.
And that kind of speed and stress demands next-generation materials. This links right back to the thermal protection systems on re-entry vehicles.
Precisely. This scientific validation accelerates the demand for advanced materials like ultra-high-temperature ceramics, UHTCs, and advanced carbon composites. These are the lightweight, heat-resistant materials that allow an airframe to sustain flight at speeds where the surface temperature exceeds 2,000 degrees Celsius without melting.
Finally, let's turn our gaze back to Mars, which saw a major scientific launch and a crucial discovery this week that reinforces the strategic roadmap for human exploration.
We saw the launch validation of commercial deep space science. Blue Origin's New Glenn successfully launched NASA's twin Escapade probes to Mars.
This validates the commercial VADR contracting model for high-value science.
It does. It demonstrates that deep space missions are no longer exclusive to bespoke government launch vehicles. Those probes are going to study how the solar wind strips away the Martian atmosphere.
But the more immediate news for future human missions came from the ESA Mars Express orbiter. What did the new research reveal?
New research based on Mars Express data provided compelling evidence of a relatively recent ice age on Mars, specifically in the Colophosate region.
Recent meaning?
The evidence suggests this ice age occurred just 300,000 to 500,000 years ago.
When you say recent, in geological terms, why is that so important for human exploration planning?
It's crucial because it fundamentally shifts our expectations about in situ resource utilization, or ISRU. A recent ice age suggests that accessible water ice, water that is critical for life support, drinking, and most importantly for producing rocket propellant.
May be found at much lower latitudes than we thought.
Exactly. We always knew there was ice at the poles, but if it exists just under shallow layers of soil closer to the equator where landing sites are warmer and safer, it dramatically simplifies the complexity and lowers the logistical cost of establishing a permanent human base.
So the science is confirming that the engineering goals of Starship and Artemis, which rely heavily on accessing Martian water, are highly achievable.
It's a powerful feedback loop.
This week was a genuine wake-up call. It demonstrated that the space industry has really matured into this complex, high-stakes operational domain where success is defined by infrastructure and resilience.
I think we can synthesize the main themes into 3 concise takeaways for you.
Okay, what's the first one?
First, operational maturity equals higher risk. The Shenzhou debris strike proves that space is no longer theoretical, it's a crowded operational zone.
And this environment requires unprecedented redundancy in rescue services, demonstrated by China's staggering 16-day response. If we commit to a permanent human presence, we have to commit equally to instantaneous rescue capability.
Second, the rise of utility is real, but technologically hard. The ASTRO contract and the focus on Xenon transfer, along with the validation of life extension services like Catalyst, are shifting spacecraft design from use and dispose to use, service, and reuse.
A shift that establishes a robust orbital utility sector, but only if we overcome that massive engineering hurdle of handling supercritical fluids in microgravity.
And third, competition drives capability. The Starship V3 setback and the new Glenn 9x4 announcement show that while the risk remains high, the heavy lift race between these massive reusable systems is fundamentally restructuring space economics.
The result is a paradigm shift, where development costs are focused on propulsion and life support, not just the cost of getting off the ground. And that accelerates the Moon and Mars timelines.
These developments signal a strategic acceleration toward what's projected to be a $1 trillion space economy by 2040, fueled by lower launch costs and the emergence of these utility services.
We're firmly in a dual-use environment.
Absolutely. Commercial capabilities, be it Blue Origin's heavy lift or responsive launch systems, are instantly applicable to defense and national security needs.
The pace of development is exhilarating, but the consequences of operational failure are rising just as fast, as the Shenzhou cruise near-miss proved.
The sheer volume of traffic now dominating LEO, from the 1.2 million pieces of trackable debris to the aggressive launch cadences, it means that regulators must either quickly adopt new, comprehensive, coordinated air traffic control systems,
Essentially treating LEO like an aviation corridor.
exactly, or risk making low Earth orbit unusable for everyone. That question of orbital governance is now the most urgent challenge we face beyond Earth.
Thank you for tuning in to Tomorrow Unveiled. We'll be back next week to continue tracking the future, one deep dive at a time.